All right, topic 9.6, coupled reactions. These are not reactions that are in a situationship. These are reactions that have, I don't know, insert stupid out of touch joke by your chemistry teacher. Coupled reactions, let's talk about it. So ultimately, we've been talking a lot about thermodynamically favorable reactions. We haven't spent as much time talking about what if they're non-favorable, right? What if delta G is positive in a direction, but you still want that reaction to happen, right? Like just because the universe doesn't want it to happen, maybe humans want it to happen, okay? Well, that means under these conditions, the reaction doesn't happen, right? It's not going to happen on its own, spontaneously. Or it's going to happen, but that equilibrium mixture is just mainly reactants. Recall that a positive delta G means K is very small. So we might have some products, but it's mostly going to be reactants, right? And that's sort of what you're seeing down here. But again, we could do something about that, right? Humans are really smart. Well, I'll speak for other humans. I don't know about me. We can add external sources of energy. So commonly, this is just going to be a battery that's sending energy into the reaction. And this is able to overcome that Gibbs positive value, that sort of positive deficit, to move the reaction forward. So the decomposition of water, thankfully, does not happen spontaneously. It's good that we have water in our cups and it doesn't just turn into hydrogen and oxygen gas. We actually don't want that to be too spontaneous. But sometimes we want pure hydrogen and oxygen gas, and this is a really clean process if we just connect electricity to the reaction. So we can use this external power source to drive a non-favorable reaction. We'll be talking about that a little bit more in the latter half of the unit on electrochem. But today we're just going to focus on coupling reactions to overcome something that's not favorable on its own. Okay? So when we couple a desired reaction that's got a negative delta G with a reaction that's got a positive delta G, we get an overall reaction that can be spontaneous. Remember, spontaneous doesn't mean fast, it means thermodynamically favorable, which means the overall delta G is negative, positive, negative, positive, negative, positive. You got it, negative. Sorry, I'm really losing it, guys. I hope you're doing okay. I hope I'm doing okay. I'm recording this February. So we've got these two reactions here. The decomposition of copper 1 sulfide to its elemental forms, copper and sulfur. Now we're told this is non-spontaneous, thermodynamically unfavorable. We can tell that by the positive delta G. We can let me just move on. With a positive delta G, if I had copper 1 sulfide and I wanted pure copper, for making wire and stuff, I couldn't just use this reaction directly to get solid copper. But if I couple this with another reaction, the overall reaction can end up spontaneous. So there's another reaction that involves pure sulfur combining with oxygen to make sulfur dioxide. This one has a negative delta G, which means it is thermodynamically favorable. This forward reaction does want to happen, whereas this forward reaction does not want to happen on its own. When we couple these, right, and that just means adding the two reactions together, we'll see an overall reaction. Now pause the video, see if you can determine how this reaction and this reaction end up turning into this guy. Hopefully you identified something, an intermediate between these two reactions, right? This guy, the sulfur, is an intermediate because it is produced in one step and used up in the next step, right? So quick note, coupled reactions, and I don't think this is written in the slide, coupled reactions must have intermediates. They must have something in common. Intermediates that actually couples them, right? It's not just like having two reactions occur in the same beaker in tandem. It's they actually have to have some substances in common. Okay, so the sulfurs cancel out. We get two reactants, the copper 1 sulfide, the oxygen gas, and two products, the solid copper and the sulfur dioxide. And that's what we see here. 2 reactants, 2 products. Now, what about the overall reactions delta G? Well, we just add the delta G's of these guys. And this is the same process as manipulating and combining equations that we've looked at in equilibrium, in acid-base, in kinetics, in thermo unit 6 stuff, right? Where if you flip an equation, you flip its delta H. If you multiply an equation, you multiply its delta H. The same is true with delta G's, right? So I didn't flip either of these equations, and I didn't multiply by any coefficients. So when I'm finding the overall smooshed equations delta G, I'm just adding those two values up, the positive 86 plus the negative 300.4, giving me an overall negative delta G, okay? So now that delta G is negative, the overall reaction is thermodynamically favorable. Overall reaction is thermofavorable, as they say in Italia. What am I saying? Okay, let's do an example. So we're given 2 reactions. We're going to write the overall reaction and determine, is this a good candidate for a coupled reaction, right? Are these 2 going to be a good match? AKA, will the overall reaction be spontaneous? AKA, will delta G be negative? Okay, looking at these, we've got zinc sulfide turning into solid zinc and solid sulfur. We've got solid sulfur with oxygen gas reacting to form sulfur dioxide. So again, I can see I've got 2 substances that would be intermediates, right? If I just added these 2 reactions together, my solid sulfurs would cancel out. So what's our overall reaction? We're going to have the zinc sulfide on the left. We're going to have that oxygen gas on the left. We're going to produce that solid zinc, and we're going to produce that sulfur dioxide gas. Excellent, excellent. So now we just need to look at those 2 delta G's. We did not manipulate either of these equations, so we are just adding these as they are. Right? So I've got a positive 198.3 minus 300.1. And I can't do simple addition in my head. That's not really that simple, but I don't want to do it. And we get a value of negative 101.8. Now don't forget, that is kilojoules per mole, right? I notice I didn't put kilojoules per mole here, but whenever we say delta G for a reaction, we mean kilojoules per mole. This guy right here tells us the overall reaction is spontaneous. So yeehaw, it is spontaneous. Yes, good example of a coupled reaction. So good example, and if I had asked, justify your answer, you would say something like, because there is an intermediate, and we have a negative delta G at the end of it. There is an intermediate in common, and delta G is negativo, for those of you who hablan español. Mic drop. 9.6, not too bad, right? Okay, just wait. 9.7 is gonna wreck your S, right?